Alright, so welcome to this video on exponential growth and decay. We're going to finish the problems that we did in the packet from class on Friday. And then I'm also going to do a couple problems from the homework section. And then you'll be able to finish the rest of the packet over a break, the rest of the break, and then we can talk about it our first day back from break. So if we look at number 3, from the notes section, that's the first one we left off with, we're told that a manufacturing company determines that once it started a new TV advertising campaign, its monthly change of sales was proportional to its current monthly sales. We were told that in the month of January, it sold 5,000 units, and in the month of April, that went up to 7,000 units. So part A asks to write and solve the differential equation that describes this relationship between time and sales. Well, we know that the monthly change of sales is proportional to the current monthly sales. So ds dt equals ks is going to be the differential equation. And we've already solved that equation with calculus, so we know that the sales would be s naught e to the kt. So we've got to plug in some values that we know, do some algebra to solve for some unknown values, and get our relationship. Well, our initial sales is going to be the sales from January, so we'll put in a 5 for that. We also know that in April there was 7,000 sales, and the time for April would be, well, we can't plug in the word April, so we need a number for that. So maybe if we make the month January T0, that would make April then be T3, because that's 3 months after. So we can do 7 equals 5 e to the 3k and solve for k. So we'll divide out the 5 and get 7/5 on the left. Then we could take the natural log of both sides. So we get just 3k. And then we can divide through by 3. So k is going to equal, as a decimal at least, 0.112. Now, here's what I'd strongly suggest. I'd strongly suggest storing k as a variable in your calculator. That way you don't have any round-off errors as you're going through the rest of each problem. And then just clear out the k and store a new one for each problem in the packet. Or create a document and then create a new problem for each problem of the packet so you can store the k continuously without using the wrong k. So this basically means then the solution to the differential equation is going to be s equals 5e to the 0.112t, where t is the number of months after January. Now, if we go to the next question, part B, they ask us how long will it take from sales to go from 10,000 to 15,000? So they're really asking us to do two things. What is the time when the sales is 10? What is the time when the sales is 15, and then figure out the difference between those two times. That tells you how long it takes to go from 10 to 15,000. So we'll start off by figuring out at what time our sales is 10,000. So we'll plug in 10 for S, and we get 10 equals 5 e to the 0.112t. Okay, we'll divide through by the 5, we get 2 e to the 0.112t. So we get the natural log of 2 equals 0.112t. Divide through by the 0.112, and I got 10.7498. Now do the exact same thing to figure out when would it get us 15,000 in sales. So we'll make S15. Divide through by the 5 gets us 3 equals e to the 0.112t. Take the natural log of both sides. Divide through by the 0.112. And we get here that t would be 14.37 months. So now we just take that difference. So we say, okay, how long is it to get from the 14.37 month mark to the 10.74 month mark, or 7498 if you want. That's how I wrote it there. That's going to be about 3.6 months. So we're approximating from the model that it's going to take us about 3.5 months for sales to increase from 10,000 to 15,000 using this exponential growth. Now if we go to the next question from the classwork section about half-life. So what we're told is the rate at which radioactive material decays is proportional to the amount present. We all understand half-life from our science classes. It's the amount of time it takes for half of the material to disappear, to decay. So we're told that we're dealing with 8 grams of a plutonium isotope, plutonium-239 to be exact. We want to know how long to decay to 1 gram. When will decay to 1 gram? Now, I'm going to show you the 2 ways to do this. I'm going to show you the duh way, I call it the duh way, and then the actual specific algebraic calculus way. So here's the duh way. This method works because of the numbers that they give you. So think about how a half-life works. You start out with 8 grams. Then 1 half-life passes, you go down to 4 grams. Another half-life passes, you go down to 2 grams. A third half-life passes, we decay down to the 1 gram, which is what we're looking for. So essentially, this is going to take us 3 half-lives to decay. Each half-life was told in the problem to be 24,360 years. So that means we expect to get from 8 grams of plutonium-239 to 1 gram of plutonium-239 in 73,080 years. It was like I said, that's the duh way of doing it, just because they asked about 1 gram. Let's say they asked maybe 3 grams. Well, you can't use the half-life. I mean, you can kind of predict it's going to be somewhere bigger than 1 half-life and less than 2 half-lives, but you want to get a precise number. So you'd have to use the function. So we'll call A the amount of plutonium at any given time. That's going to follow the exponential model of 8e to the kt power. All right, well, if it's a half-life, then that means in 24,360 years, the 8 grams reduces to 4. So we'll plug in 4 for A, we'll plug in 24,360 for T, and we'll solve for K. So I get 1/2 is E to the 24,360K. The natural log of 0.5 equals 24,360K. And then you can divide both sides by that half-life. And you get your K value. Okay, I'm not even going to type that out or write it out because it's a very small number. What I would do is I would store it in my calculator, and then from there, you can solve the equation 1 equals 8e to that K value, which we know would be a number now, not a second variable, times T. When you work through the algebra, you would still get that T equals 73,080. Okay, so that would work. Now that we have that K value, I could ask you anything. I could say, when would it decay to 1/3 of a gram? When would it decay to 5 grams? Things that aren't as obvious using the half-life the way the problem was worded, and you'd still be able to get me the answer. Now let's start taking a look at the 2 questions from the homework section of the packet. So the first one is about car depreciation. So as most people know, when you buy an expensive thing like a car, the value is going to go down over time. It depreciates is what it's called. So we're told in the problem that the change in a car's price is directly proportional to its current value. And we're told that suppose you own a car whose value is currently $9,000, and 6 months ago, the trade-in value was $9,500. So we want to write and solve a differential equation that expresses the trade-in value starting 6 months ago. So that's part A. So we're starting at that 9,500 point. All right, so the differential equation that we're writing, you should be very good at these by now. dP over dt equals Kp, where P is the price, which then, from the calculus we've done before, means that the price at any given time is going to be P naught e to the kt power. So we need to figure out P naught, we need to figure out K, and we have our function. Well, we're deciding that we're starting at 6 months ago, so 9,500 is going to be our P naught. So we get P is 9,500 e to the kt. And then we've got to use this second point. So 6 months later, T is 6 if we make T months. At t equals 6, p is 9,000. So we'll put 9,000 in for p. We'll put 6 in for t. And now we get the equation 9,000 equals 9,500 e to the 6k power. And we can solve for the k. So we'll divide both sides by 9,500. We'll take the natural log of both sides. And we get that the natural log of 9,000 over 9,500 all over 6 equals k. Okay, and I tell you right now, this is one that would probably be worth storing on the calculator because you end up getting a really small decimal. I get negative 0.009011, and it keeps going. So that's going to be our function. So that means p is 9,500 e to the negative 0.0090t, if I just keep it at 4 decimal places. And this makes sense that the k should be negative, because remember we talked about that as well, and it's in the packet. When you have exponential growth, your k is positive. Okay, when you have exponential decay, your k is negative. So if you think to, in the 2 examples we've done already, the sales problem, k was positive because sales got larger as time went on. If you think about the half-life problem, the k was negative because you were losing the amount of atoms in the radioactive material as time went on. So that's our function, and we're basically going to use that function to do B, C, D, and E. And these are mostly algebra problems, each of these parts. So part B just asks, okay, what's the trade-in value going to be 6 months from now? Now, the thing you got to be careful about is the variable. Remember, time 0 was 6 months ago. So 6 months from now is going to be t equals 12. Because we used, the present value was 9,000, and we used t equals 6 for the present value. So that just means we're going to plug in 12 for t. Well, that should be 9,500 first. So p is 9,500 e to that negative 0.009011 times 12. Now again, this I stored, so that way I get an exact answer, and I strongly suggest you do that. So if you store it and you plug in 9,500 times e to the 12k, you would get a value of $8,526.12. Okay? Now if we go to part C. Part C wants to know, basically, once you know that the car's value drops to $6,000, you're going to sell it. So when does that happen? So we set the value, the price, to equal to 6,000, and we solve for T. I'm just going to write K, just so you all don't feel like carrying through that decimal, but understand that that K is really a value. So we'll divide through by 9,500, and I'm going to reduce that to 60 over 95, which you're allowed to do. We could have done that earlier, too, when we were solving for K, equals e to the kt. So the natural log of 60 over 95 equals kt. We'll divide through by that constant k, and then I got that t equals 50.995. Now the thing you've got to be careful again is this was 50 months from when the original value was 9,500. So you really have to subtract 6 from this and get 44.995, because everything is really relative to that 6-month period. So that means basically at about the 45-month mark from now, or in other words, about 51 months from when it was valued at $9,500, we would sell this car and expect to get $6,000 in value. Now part D is interesting because this is going to kind of change your perceptions of values for time. So the question says, at the time your car was worth $9,500, it was 5 years old. When was its trade-in value when it was new? So the car was 5 years old at a value of $9,500. What is the new value? Brand new value. This means we've got to figure out what am I going to plug in for t. So we're saying when it was 9,500 in value, that was the 0. We're going back in time 5 years, or 60 months. So you guessed it, you can actually, for this problem, have to make time negative, and you have to set it equal to negative 60. So that represents 5 years ago from the $9,500 value point. You're allowed to do that with exponential decay like this because we're basically working backwards in time. I mean, technically you could use time to be a negative value, but usually our initial value is 0. Like, you're running a race, time is 0. You can't go back in time because prior to that you weren't running the race. But in this case, we're talking about the fact that we're dealing with a used car that at our 0 point, when maybe we say we bought it, it was already 5 years old. So our t equals 0 is really 5 years old for the car. So if we plug in negative 60, we can go back those 5 years to when that car was originally brand new. Alright, so we will do that. So we will say that that price is going to be 9,500 times e to the negative 60k. Again, remember, k is stored in my calculator. And when I type that in, I get a value of $16,313.03. So when it was brand new, that was its trade-in value. Now, E really is no calculus, so we will just talk about that a little bit. It's more one of like an economics sort of question. So E says the purchase price was $18,000. Why is that different than what we just calculated in D? And frankly, you may have talked about this in a business class, or you just may know this from your own experience. One reason why buying a new car is sort of a terrible investment, though it's one that we all need because we need to get from place to place, is as soon as you purchase that car, it depreciates in value. So sure, a brand new, never been owned car that's worth $18,000 might drop in value to $16,313 just by virtue of the fact that you have now bought it, and it is now called a used car. Okay? So that's the reason why the value is different, even though we used the initial time that that car was purchased. Now, if we look at the second homework problem about carbon 14, so essentially, the whole point of this, and this comes up with a lot of stuff with archaeology and the like, carbon 14 is an isotope of carbon that is in trees and a lot of other things. And the rate of carbon-14 decay is directly proportional to the amount present, as it says in the statement of the problem. So that's one way that a lot of historians and archaeologists and scientists can date some different artifacts and fossils to determine how far back in history those things are from. So if we look at part A, it talks about this pine tree in the White Mountains of California. It is the oldest known tree. It is 5,065 years old. We are told that if the half-life of carbon-14 is a whopping 5,750 years, what percentage would we expect to find in this tree if we went and we took took a sample of its innermost ring? So we've got to use this fact of the half-life to figure out what the K is and then come up with some sort of function that will help me figure out the amount of carbon-14 in this tree. So we know the amount of carbon-14, we'll call that A. That rate that it changes is directly proportional to the amount present. So if we solve that differential equation, as we have for a couple times now, that means it's going to be equal to the initial amount of carbon-14 times e to the kt power. And we need to figure out what k is. So we're going to use this half-life notion here that I have written, I'm boxing it in now, to figure out the k. And they actually give you a hint in the problem about it. They say 100 units of carbon-14 will decay to 50 in 50 years. So that means at the time 5,750, the amount, if the original amount was 100, will now go to 50. And we can use that to solve for k, write an equation that contains only k. So 50 equals 100 times e to the 5750k. You know, if they didn't give you that information, you could also make the original amount 1, and then make the amount on the left side of the equation 1/2, half-life. It really doesn't matter as long as a naught is double a. You'd still get the same value of k, because look what happens. We're going to divide by 100 anyway, and we're going to end up with a half on the other side. So 0.5 equals e to the 5750k. We'll take the natural log of both sides. You'll notice that this is very similar to the last problem with some different numbers. We still have the natural log of 0.5 on the top. Okay, so the last half-life problem we did, basically the only change is we're using 5750 because we're talking about the half-life of carbon-14, as opposed to 24,360, which was the half-life of the plutonium from that problem in the classwork section. Okay, I'm going to tell you right now, if you haven't been storing values in your k's on the calculator when you're doing these, I strongly suggest it for this problem. Because when you do the natural log of a half divided by 5750, you actually get a k, at least on my calculator. I got scientific notation. I got negative 1.205 e to the minus 4, which is times 10 to the negative 4. That is a really, really, really small k value. And that makes sense considering we're dealing with half-lives and it takes a really, really long time for radioactive isotopes to decay. So this will definitely get stored, and as I do the rest of the problems in this section, I'm going to use k, but realize that I'm talking about this number. So that basically means when we're dealing with carbon-14 dating, that's going to be our k value, which is helpful now because now I can use this for the Gargi pine tree problem in part A. So we can say that the amount is going to be E, really 1E, because I want to get a percentage of carbon-14. So if we started with 100% when the tree first grew, that would mean 1 would be my A naught. E to the K, and then the T I'm going to put in is the age of the tree, which is 5,065. And since I have K stored in my calculator, I can literally do E to the 5,065 times K power, and I got 0.543. So we'd expect 54.3% of the carbon-14. And that makes sense because it seems like this tree is just a little bit less than a full half-life, so we would expect to get just a little bit more than half of the carbon-14 because it's still in the process of decaying. Over the next, 600 years, we'll see that other 4.3% decay away. All right, so that's part A. Part B, now they're going to ask us to be kind of amateur historian archaeologists here. A piece of wood claimed to have come from the Ark of the Covenant is found to have 69.1% of its carbon-14. It has been suggested that the Ark was created in 1290 BC. So we want to use the math and determine if there's evidence to suggest that this wood is old enough to have come from the Ark of the Covenant. So what we have to do is, well, we know that it has 69.1% of its carbon-14, and this is exactly how people in the field do this dating. They say, okay, I have my amount, I know my half-life, so I know my k value from my exponential function. Well, what's t got to be? So we know that A is going to equal A naught e to the kt. In this case, again, we're dealing with a percentage of carbon-14, so we'll deal with this as a decimal. So that means I have 0.691 of the carbon-14 remaining if A naught was 1. Okay? So then that means the natural log of 0.691 has to equal k times t. And again, we do know what k is, so even though I'm using a variable here, I'm just saving myself from writing that big long decimal. So you can type this into your calculator just as I have it written here if k is stored, and you will find out that t is about 3,066. It's approximately equal to if we just cut off the decimal places. So that means this wood is 3,066 years old. Is it old enough to be part of the Ark of the Covenant. Well, let's see. How many years has passed since 1290 BC? This is where you got to be very careful about your BC versus AD. So to get from 1290 BC to the year 0, that's 1290 years. And then to get from the year 0 to our current year of 2016, that's another 2016 years. So if we add them up, we get 6. Carry the 1. We get 3,306 years between when we believe the Ark of the Covenant was created and our current year of 2016. So, unfortunately, this wood is just a little bit too young. We're dating it at 3,066 years old. We need it to be another 300 years old, roughly, so it needs to have a little bit less carbon-14 for us to be convinced that this wood came from the Ark of the Covenant. Okay, so that's our second example of how we can use exponential growth and decay. You have a few more other problems very similar to these with some other applications. They're all going to basically flow the same way, so feel free to rewatch any of these problems if you want more examples. There's not too much calculus here. We're really winding down our study of calculus, and this is a nice review of some algebra and pre-calc with exponents and logs. Okay, if you have any questions, feel free to ask me. Otherwise, thank you for watching.